Welcome back. Today's goal of this lecture is, today at first I will see if AK converges to the matrix A as K tends to infinity in M and R. AK is the matrix, so obviously this is converges in M and R. Then for any M belongs to natural number, I will see AK to the power M converges to actually A to the power M. Then I will see three new matrices, GL2, SL2 and orthogonal matrix which is denoted as ONR. And we all of us know what is the GL2, what is the SL2 and what is the ONR. GL2 is the matrix. Here I have considered 2 cross 2 matrix. GL2 is those matrix whose determinant is non-zero, and SL2 are be those matrix whose determinant is 1, and orthogonal matrix means A transpose equal to identity. Today I will see GL2R is open in M2R, SL2R is closed in M2R since I have considered 2 cross 2 matrix, and orthogonal matrix is closed in M and R. Here I have considered n cross n matrix. This is our goal of this lecture. Actually, this concept is very important concept. So, please take some time out and try to learn the topic from this video. And save the video with you and keep watching it every small interval. Okay? Let's come back our original discussion. At first, I will see this proof. If AK converges to A in M and R, then for any M belongs to natural number, AK to the power M converges to A to the power M. For this, if AK converges to A in M and R, I will prove AK to the power M converges to A to the power M. For short calculation, at first I will prove AK square converges to A square. For this, consider AK equal to, here the sequence as a matrix. So consider AK equal to AK, BK, CK, DK. And consider A equal to ABCD. Since given AK converges to A, therefore small ak converges to A, small bk converges to B, small ck converges to C and small dk converges to D. Then we have to prove actually AK square converges to A square. For this, AK square is this matrix and A square is this matrix. Since we have to prove AK square converges to A square, so to prove this, I will prove norm of AK square minus A square tends to 0. For this, norm of AK square minus A square, since here the metric space is R, so in this metric space, here the norm is Euclidean matrix. So norm of AK square minus A square would be small ak square plus bk plus ck minus A square minus bc whole square plus ak bk plus bk dk minus ab minus bd whole square plus ak ck plus ck dk minus ac minus cd whole square plus bk ck minus dk square minus bc minus d square to the power whole square to the power 1/2. And since here we can write this as ak square minus A square plus bk ck minus bc. Just rearrange this part, and I have written this part in such type because AK converges to A, BK converges to B, CK converges to C and DK converges to D. This is given in my hand. Similarly, this part we can write this as AK BK minus AB plus BK DK minus BD whole square. This part written as AK CK minus AC plus CK DK minus CD whole square. And this part we can write BK CK minus BC plus DK whole square minus D square. And from this given expression we can write, obviously, this part goes to 0, means norm of AK square minus A square, this norm tends to 0 as K tends to infinity. And that implies AK square goes to A square. I hope my all viewers have understood. And by induction, since AK goes to A, similarly AK square goes to A square. Therefore, by induction we can tell AK to the power m goes to A to the power m. Okay? Prove that GL2R is open in M2R, where GL2R is set of all 2 cross 2 matrices such that whose determinant is not equal to 0. And we have to prove this is open. For this, we have to prove complement of the set is closed. Consider F equal to complement of the set G, means M2R complement G. Since this is the complement, so this is equal to set of ABCD such that AD minus BC equal to 0. We have to prove this is closed, and if this is closed, then our given GL2R always would be open, and consider the set as F. Clearly, F always contain F closure. For this, take one arbitrary matrix in F closure, take A equal to ABCD. Then, always there exists a sequence AK in the set F such that AK converges to A, where AK means obviously such type of matrix AK, BK, CK, DK, where K belongs to natural number. Since given AK converges to A, that implies obviously small ak converges to A, small bk converges to B, small ck converges to C, and small dk converges to D. Okay? Means this ak belongs to the set F, where F means such set whose AD minus BC equal to 0. Therefore, AK DK minus CK BK would be equal to 0. Okay? And also AK DK minus CK BK means AD minus BC. These two expression I have got AK DK minus BK CK converges to 0 and converges to AD minus BC. But we all of us know limit always unique. So actually AD minus BC equal to 0. Okay? And since I have got AD minus BC equal to 0, that means A, which is equal to ABCD matrix, this is actually belongs to F. Therefore, I have taken A belongs to F closure and I have got A belongs to F. Therefore, F closure contain F. And always F contain F closure, therefore that means actually F equal to F closure. So, since F equal to F closure, that imply the set F is closed. Okay? I hope my all viewers have understood. Since F is closed, that means since F is complement of GL2R, that means our given set GL2R is open. I hope my all viewers have understood clearly. Okay? OL. Second, I will say SL2R, which is actually equal to A belongs to M2R such the determinant of A equal to 1. I will say SL2R is closed in M2R. For this is actually exercise. I hope my all viewers have understood how we have to prove. We have to prove this set is closed. Actually, consider F equal to SL2R and we have to prove F equal to F closure. Clearly, F contain F closure. Now we have to prove F closure contain F. For this, consider A belongs to F closure. That means obviously there exists a sequence AK belongs to F such that AK converges to A. What is AK? Let AK equal to small ak, bk, ck, dk. This sequence, consider the sequence as such type. For all k belongs to natural number and A equal to A, B, C, D. Okay? Converges to A means obviously small ak converges to small a, small bk converges to small b, small ck converges to small c and small dk converges to small d. And by this expression AK dk, since the set is determinant of A equal to 1, AK dk minus BK CK equal to AD minus BC, similar to before. And since AK, I have considered AK from the set F. AK belongs to F. F means determinant of A equal to 1. Therefore, that imply AK dk minus BK CK equal to 1. That imply actually AD minus BC equal to 1. Therefore, I have got AK BK, AK dk minus BK CK converges to AD minus BC. Also, I have got AK dk minus BK CK converges to 1. But we all of us know limit is unique. So, by uniqueness of limit, that implies AD minus BC actually equal to 1. And AD minus BC equal to 1 means obviously, notice this is A and AD minus BC equal to 1 means determinant of A equal to 1, and this is actually our given set SL2R. Therefore, that proof that imply A belongs to A. But I have considered A belongs to F closure, and I have got similar to before, A belongs to A. Therefore, F closure contain F. Clearly, F contain F closure, and I have got F closure contain F. So, obviously, F equal to F closure. So, our given set SL2R is a closed set. I hope my all viewers have understood the question clearly. Okay? Well, next example, I will say orthogonal matrix is a closed. This example is similar to before. Try to oneself. Just as a review, I have solved this question again. But at first I will highly recommend you please try to oneself. Here we have to prove similar to before, F equal to F closure. Clearly F contain F closure. Now we have to prove F closure contain F. For this, let A belongs to F closure. And A belongs to F closure means obviously that implies there exists a sequence AK who is contained in F such that AK converges to A. And if AK converges to A, then that implies obviously AK transpose converges to A transpose. So, AK times AK transpose converges to A times A transpose. Okay? And since AK belongs to F, that means F means orthogonal matrix. That means obviously AK transpose equal to identity. Okay? That imply AK transpose converges to identity. Here I have got AK times AK transpose converges to AA transpose, and here I have got this is converges to identity. But since limit is always unique, that means obviously this AA transpose nothing but this is actually identity. A transpose equal to identity. That means A is orthogonal, and since A is orthogonal, that means since F is collection of those matrices which is orthogonal, so obviously A belongs to F. Therefore our proof is done. I have considered A belongs to F closure, and here I have got A belongs to F. Therefore F closure contain F. From this and from this, that imply F closure equal to F. And since F closure equal to F, therefore our given set of all matrices which is orthogonal is a closed set. I hope my all viewers have understood how we have to prove any closed set by closure property. Okay? This type of concept actually very important for higher study. Okay? Well, today I will stop here. In my next video, I will see GLNR. I have seen at first GLNR is open set in a manner. In my next video, I will see GLNR actually dense it in a manner, and this type of proof also very important. But at first I will tell you, please see today's video with pay attention, because this concept is very important for higher study. See you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.